So in the last class, we saw some arithmetic circuits. Basically, we saw various kind of adders. Today we'll continue with the arithmetic circuits. We will see multipliers, shifters, and comparators in today's class. Right. So how do we do a normal binary multiplication? Right. Like suppose you have 1 0 1 0 1 0 to be multiplied with 1 0 1 1. Normally what we do is, if you do an hand calculation, if there is a 1, this thing is repeated as it is in the bottom, right? And then we are shifting the next one towards the left, or you could say this is being shifted towards the right. Okay, and then subsequently you take the next significant bit out here from the multiplier, and if it is 1, you just replicate what is written here, right? So what is this? Actually, this is an AND operation of this and this, right? So if you see here, 1 0 is 0, 1 1 is 1, 1 0 is 0, 1 1 is 1. So what is this? This is actually an AND operation. And similarly, if it is a 0 here, everything comes to be 0, and that is also an AND operation. So if we can say that the partial products, okay, all these are known as the partial products. Now they are obtained simply by doing an AND operation of the individual bits. Okay, so that is how it. And on the thing is, once an AND operation of the entire multiplicand is done, then we need to make a shift operation. Okay, so that's the thing which is to be kept. So there is an AND operation involved and an shift operation involved. Okay, and then obviously here there are finally, after the and the shift, the way it is arranged here, you need to have adders which could add all these things in the vertically. So these are the three things which we need to do to make an to implement it in hardware. Okay, and there should be some arrangement where these things are shifted, and then you should have adders. Okay, so let's see how it can be done. So this is the first multiplier topology which we are going to see today. It is known as the array multiplier. Okay, so these are the partial products which I have written here from like this is A0, B0. So I am taken an example of 4 into 4 multiplier. Okay, so A0, B0, A0, B1, A0, B2, A0, B3. So similarly A1, A2 and A3. So 4 into 4 multiplication. I have just taken an example here. So how to implement that? So if you see here, A0 B0 is just an A0 B0 can straight away come as a P0. P0 indicates a product 0. Okay, and this indicates an AND gate. Okay, so all the so to just to keep the diagram simple, I have not indicated the AND gates. Okay, so all these A2 B2, A2 B2 or A2 B0, A3 B0, all these are actually in the hardware, they are all simple AND gates. Okay, so those AND gates have not been represented here. Only the half adders and full adders have been. So if you see the next here, there are only 2 bits to be added. So this comes straight away down. Here only 2 bits are to be added. So I have an half adder. So these can be added, and the product can be taken. Okay, the next significant product which is called as P1, and that is taken straight away here. Now there will be a carry generated, right? So that carry needs to be sent to the next stage. So I have this arrow which, so I instead of a full adder, now I am going to have a half adder. Instead of an half adder, I am going to have an full adder here in the next stage. Okay, in the next stage, if you see here, what are the things? I have A0 B2, A1 B1, so they have been written here, and the carry which was coming from the previous stage, so one full adder, and then I also have A2 B0, right? So that also needs to be added. Now I can use an half adder, because in this stage only one sum which is coming from the previous stage is there, and this is the additional 10. There are only 2 bits to be added. So I have used an half adder out here, and then the next partial product comes down, right? Now they could be a carry from here as well. So they are propagated horizontally out here. And then you have one more full adder. Here there are 4 bits out here. right, which needs to be added. So 2 are taken care of here, and this carry is taken care of here. Again you have one more a full adder, because this carry is taken care of here, and the third bit is taken care, and then you have one more half adder with the fourth bit is taken care of here, and then obviously there is no carry coming, so you just can use a half adder, and then you have the next product. So you keep expanding that. Here I have I can use just an half adder, because there is only one carry which is coming from here, and there is only one bit which is because I need to use an half adder here, full adder here. So only one bit is used here, so one bit is used here, other two are used here. So I have a full adder and a full adder here, and the carries are being taken care of in these conditions. So you can swap this these full adder and a half adder also. This last you can have an half adder here, you put a full adder here, and you take an A3 B3 to the top. Okay, so that also can be done. So but essentially this will remain one half adder and two full adders in this vertical chain. At least that much will be required. So you get one more partial product, and then here there are 2 bits to be added, and carry from here also. This carry needs to be catered for. So all these carries, so you just keep expanding it till you get a total partial products. Okay, so when you do an 4 into 4 multiplication, total you will get 2 into 4 2 into 4 that is 4 plus 4 minus 1, that is total 7. There will be 7 partial products. Okay, so similarly if it is 4 into 3, then you will get a 4 bit into 3 bit, then you will get 6 partial products. So 4 into 4 will give 7 partial products. Okay, so this is so this is what. Okay, so there will not be an further here, because this is a full adder. Okay, so this is going to give sum, and this is the carry. Okay, so this P7 is the carry itself. Okay, this represents the carry out here. Okay, so this is the structure. Now in this structure, okay, there is, this is not used in practical circuits, because it has got certain disadvantages. So that is shown out here. Okay, first is this we already discussed, the total number of partial products if you are doing an m bit into n bit multiplication will be n plus m minus 1. Okay, so since we did an 4 into 4, it will be 4 plus 4 minus 1, 7 partial products. Okay, so that's it. We have just taken one particular example. Okay, now the disadvantage here in this particular topology is, if you try to find out the max delay chain. Okay, so you have here, it's coming here, it's coming here, it's coming here, here. So this is one path where you have the max delay. Okay, you can call it as a critical path, right? There is also one more critical path. Okay, it can go here, it can come here, it can come here, it can come here, like this, right? Or it could come here, and I have just shown 2. It can come here, it can come here. So this particular circuit has got multiple critical paths, or you can say that almost all the blocks are kind of critical only, right? So for this particular topology, if you have to optimize it, okay, then you will have each and every block you might have to optimize it. So that will result in high power consumption, right? If you try to target the delay of each and every block here, so that is when we see other topologies, we will see that is not the case. Okay, so now if you see here, although it is shown like this, okay, in the actual layout, what is this? This is an 4-bit adder. Okay, this is also a 4-bit adder. This is also an 4-bit adder, because we did an so how many 4-bit adders are required? N minus n m bit adders are required. So you are doing a multiplication m into n, right? So like if you are doing it, so you require an m bit adder, and if n is n minus 1, such adders will be required. right? In this particular case, we did an 4 into 4 multiplier, 4 into 4 multiplication. So we required an 4-bit adder, and since it was 4 into 4, 4 minus 1, 3 such 4-bit adders have been used. Okay, so that is what. And also you require m into n AND gates. Okay, so because all these partial products which I have written here, I have not shown the AND gates. So m into n AND gates will be required. You require n minus 1 m bit adders. Okay, and now if you try to find the delay out here, okay, so whatever is shown in the horizontal is carry delays, and whatever is the shown in vertical out here, okay, they are the sum delays, right? This sum is coming here. Horizontal is the carry delay. So you will find n minus 1 t sum, okay, and n minus 1 plus n minus 2 t carry and t AND. So this is the formula that is used to compute the total delay. Now t AND means AND every bit, so one AND bit delay is there. Okay, now sum, if you see here, 1, 2 and 3, right? So this is 4 into 4 bit multiplication, so 3 sum delays is there, right? Now this is 4 minus 1 is 3 and 4 minus 2 is, so 5 carry delays are there here. So 1, 2, 3, 4 and 5. So 5 carry delays and 3 sum delays and 1 AND delay. So this particular structure, this is how you compute the delay. Is it okay till here? Yeah, okay. Now this particular circuit, okay, this is just an reorganized out here. It is known as a carry save multiplier. Okay, so here instead of propagating the carry horizontally, like within this 4-bit adder, okay, no carry is propagated. Okay, this is the 4-bit adder, right? So the carry is propagated from each of these blocks into the next block. Okay, so if you see here, this carry is coming here, this carry is coming here, this carry is coming here, right? This carry is coming here into the next block. Okay, so everything is done here. So same kind of, only thing is the way it is the carry is the way carry is connected is different. It is the same block, only thing is this carry, instead of going here, it is coming here. So this becomes an full adder in this case. So this becomes an full adder, and since there is no carry here, this was a full adder, that becomes an half adder. Okay, so these are all become an half adder out here, and since it is coming out like this, so these have become full adders. Okay, right? You had an half adder here, but with this signal, now this carry is going to come here, so there are now 3 bits this adder has to cater for. So that is the reason this has become now here an full adder. Okay, so the advantage of this particular circuit is the propagation delay. Okay, the critical path is now well defined. Okay, it comes like this. It comes from here to here, and then it goes here. Okay, this is not, if you see here, this is not the critical delay, right? This is the critical delay, because you see here you are missing one particular chain. So this is the critical delay in this particular path, right? So this is the advantage of having an carry. Now if you have this particular path as a critical path, then you can optimize the design. Okay, you can optimize probably these designs. You can leave aside all these blocks and just think of optimizing these delays. Then you can make this thing slightly faster than the routine. Okay, now see, if we are just leaving 1, 2, 3, 4, 5, 6, 7, 8, 9. This we are talking in terms of just an 4-bit into 4-bit. Now if you think of an big adder, then the block, now this is just an 4-bit into 4-bit adder, right? So if you are thinking of an 8-bit into 8-bit, so you can think the critical path will be only in the corners, and the rest of the whole setup, we don't have to bother about optimizing the size. Okay, so the savings will be much more. So you can just target and try to make this particular full adders, these 3 1 half adder, 2 full adders, and this chain faster. So if you do that, then again this requires the number of adders is the same from the previous topology, require n m bit adders and require m into n AND gates, but now the delay can be called as a T and n minus 1 carry. So 1, 2, 3 carries are there, and T merge. Okay, so this entire 4-bit adder here is called as T merge. It is known as a vector merging adder, in which this is optimized for speed and not for power consumption, and so hence we call the entire delay of this block as T merge. Okay, so this is known as carry save multiplier. So among the combinational designs, so this is one of the good designs, you could say. Okay, now although in both these topologies you are seeing that they have been shifted like this, but in actual layout, okay, you can just stack all this in a vertical manner. Okay, so you don't have to, that is only just for understanding purpose, they have been shown in an offset manner. So otherwise the routing will be like this. Okay, so this will be the optimized half adders, and otherwise this will be the kind of layout for it. This is the multiplier floor plan, right? Okay, now before me taking on to next kind of adder, let's just this transmission gate, you might have done it in your VLSI class. So let's just revise this particular circuit. This is known as a transmission gate XOR. Okay, now what it does, this is the output F. Okay, so when A is 0, right, if A is 0, okay, then there is two possibilities, right? Like B is 0. If B is 0, A is 0, this is switched on. If B is 0, so nothing would happen, right? So this you have a 0 coming here, right? Okay, and this is an this will be switched off. A is 0, and if B is 0, this will be switched on. So this F will be, if A is 0, B is 0, F will be 0. But if A is 0 and B is 1, then this is switched on and this node gets charged to 1 out here, right? So you will find this working as an XOR gate. Similarly, if A is 1, so this will be switched on, and if B is 1, so this will be 0 out here. So this is, since this is switched on, this node will be discharged to 0, and if A is 1 and B is also 1, so this will be switched off. Now if you find it here, from here, if A is 1 and B is 0, and that is the condition we are discussing, right, then this will be switched on and this F will get charged from through A to here. So this works like an XOR gate. So this F out here is the output, A and B are the inputs, and you get an XOR output out here. Okay, so this is how a transmission gate and XOR works. So in adder cell, in a multiplier, in an array multiplier, right, we have these multipliers, right? So how does that these blocks inside look like? So that is being shown out here. So what we have, this we did in the last class, right, where you have a carry, and then you have a generate signal, and you have a propagate signal which generates the carry, right? So how it is being implemented is, you have A, you have carry, so you have A bar and carry. Okay, and you have a propagate signal being generated here, okay, inside the block. So so you have why we are discussing this is, right, these full adders, right, these full adders are not 28 transistor and full adders which are generally being used, okay, inside this block. We studied about 28T transistor full adder CMOS transistors, like. So we are saying that a much better option is available for us to implement these full adders, okay, inside each of these multiplication block. So that is what is being shown out here, right? So you have an A bar and C bar being generated, and this is an exclusive OR gate, right? So if you see, this is what we studied here, this XOR gate, and there is the same XOR gate which is shown out here. So you have inputs A and B, and A XOR B is nothing but the propagation signal. So this is a propagation signal, and you are also generating propagation bar also out here. Okay, how are we generating propagation bar? But just by inverting the signals, right? You are giving an A to the NMOS. Okay, now here A to the PMOS and A bar to the NMOS. Here you are giving A to the NMOS and A bar to the PMOS. Okay, so you are just inverting it. Similarly, here B is B you find. So if you just invert these signals, you will get the propagation bar signal also, right? So propagation and propagation bar signal is being used out here. So once you generate propagation bar, you can generate a carry, right? So it is like propagation. Here if you see here, propagation is this propagation bar. Here propagation is coming out here, and carry bar is coming here. So propagation and carry bar means there is no carry here. So you are using an inverter. So this will become a carry out here, right? Propagation and carry bar. Okay. So you are allowing it to transmit from here. So this is similarly the sum has been generated here. Sum is from propagation, XOR of propagation and carry. Right, so similarly, you are making an. So if you see, this is how the adder blocks are implemented for multipliers. Okay, so what is different out here is the identical delays for carry and sum. One is that it obviously, since we are using pass transistor logic, the number of transistors required out here is less. That is one advantage. Secondly, the carry and the sum propagation delays are same, right? Like here, because unlike a ripple carry adder, the only carry is being propagated in those cases, right? For addition, whereas the sum is not being propagated. Here for a multiplier, you will find that the sum is also being propagated. Like so sum is also as equally important as an carry also. So carry and sum both are equally important for a multiplier, and that is the reason why we have thought of a different topology, which is faster than the normal sum and carry 28 transistor topology. Here both and sum and carry are optimized. Okay, so this is the kind of adders which are pass transistor based logic full adders, which are used as building blocks in multipliers. Okay. Now you can also have a sequential multiplier. Sequential multiplier is nothing but it is a clocked based register based multiplier. Okay, here again, and this is the same. If you understand the multiplication, what is done here is if it is a 0, we write zeros. If it is a 1, we write this entire thing out here as it is, and we keep shifting it towards the left, or you can say we are shifting it this towards the after checking. If it is 0, we just write 0 and then shift it to the right, and I take the next bit. If it is 0, I write all zeros and then again shift it to right. Okay, and then I take the next bit. If it is 1, I write this entire thing out here as it is. Okay, so this is how, and then you keep adding it. Okay, so this can be implemented with a simple shift register add an adder. So that is shown here. Okay, now if you see here, one data is put here into the multiplier. Okay, one data, and the multiplicand is put out here. Right, this is an n-bit adder. Okay, and initially this accumulator will be loaded with 0. This accumulated initially will be 0. So the 2 bits which requires to be multiplied, one is put here as q0 to qn minus 1. The other one is put here m0 to m minus 1. Okay, so these are loaded with these two data out here. Okay. Now let's see how does this work out here. So first it is sampled. This particular data is sampled. Okay, if it is an 0, okay, if the leftmost data is 0, what I do is this is a multiplexer. So the control command is given here. Okay, so this multiplexer can push 2 data into the adder. One is 0 as it is, or 1 is the multiplicand, right? So initially this is 0. So if the first bit is 0 here, it is going to put another 0 out here, right? So and then during the first positive going edge of the clock, this data will be loaded into the shift register, right? So this data gets loaded out here, right? And in I can say the optimum way to use this circuit is during the negative edge of the clock, during the positive edge of the clock, say I am loading the data, and during the negative edge of the clock I am going to shift this data to the right. So once I have this data coming here, I will be shifting it to the right in the negative edge clock. Okay, so what I have done, based on whether it is 0 or 1, I have added either 0 or the multiplicand itself. Okay, now I take the next bit out here. Okay, next bit. Now again I will check whether it is 0 or 1. If it is 0, right, what if you see here, right, I am checking here this A, right? Every time I am checking this A, if it is 0, I am going to add a 0, and if it is 1, and then I am shifting this A slowly towards the right. Okay, this A I have loaded it. Okay, sorry, this A I have loaded it here, and every time I am shifting this towards the right. So I am now checking the next bit. Okay, so that is what I am doing here. So now the next bit is checked out here, and if it is 1, then this multiplicand. What is multiplicand? Multiplicand is this data, this B data is here. So every time there is a 1 out here, this multiplicand is going to be added into the adder. So if you once you finish the cycle, n bit cycle, you will find that the final result will be available in this whole register as this from a n minus 1 to q0. That can be considered as an single register. Okay, and the entire result will be available here. So you are just taking, so this slowly keeps getting as you keep checking the 1 by this data, this A, you are checking each data and you are pushing it right. Finally this A gets out of the register, and whatever is the result which we are doing here, an addition, and that keeps coming, and that will be available here. So the final answer will be available here. Is this algorithm clear to all of you? Yeah, Abhishek Srinivasan, is it okay? Okay. Okay, so if I take one example, it will be now further clear. Now suppose I have to do 3 into 5 multiplication, right? So this is m 0 1 1 1. M is this. Okay, so this remains constant. This data is not going to change. Okay, this is going to remain constant. So this is 0 0 1 1. And initially accumulator is all 0. Accumulator is this you are going to preload it as 0, and this is the Q is this register where we are going to put the next data which requires to be multiplied. So this is 0 1 0 1. So this is 3 and this is 5. So if you see here, we are going to sample this first bit. This is 1. That means this is 1 out here. So we are going to the n bit adder, this multiplexer is going to put this multiplicand, not 0. If it is 0, it will add 0. Since it is 1, it is going to add the multiplicand. So during the positive edge of the clock, this added data is already available here, right, from this data. So that will be loaded into this register. So I am telling during the positive edge of the clock, this m has been added to A, and it gets loaded into the A. So 0 0 0 1 1. So this is the first operation, and then you have to have an immediately after the load, you have to have an shift right register. So during the shift right operation, so during the negative edge of the clock, I am saying m will remain like this. This data gets shifted. So from here, this second one has come out here, and I have an 0 out here now. Now since it is an 0 out here, so I am going to sample this 0 in the next cycle. So it is 0 out here. So I am going to add 0. So this accumulated data doesn't get changed. Okay, since I am adding 0, so this remains as it is. Okay, and then I am going to make another shift right operation. So this one also has come here. So this has again become 0 0. So this has shifted. So I have 1 here. Since I have 1 here, in the next cycle I am going to add these two out here. So I get again 0 0 0 1 1 here. right? And then I'm going to do a shift operation again. Among these two ones, one is remaining here, the one has come here, so this becomes 3 1 and a 0. It's a 0 out here, so I'm going to add as it is. No, I'm not going to add anything, so this remains in a 0 0 0 1. And this also remains the same, and then you are doing a shift operation, so you are getting this answer. Now if you see, this is 15, right? So 3 into 5 15. So in 4 clock cycles I am getting the answer. Now if you see here, hardware wise, you can imagine, okay, if it is a 64-bit and an adder, okay, a multiplier, you see the kind of hardware which will be required here for 64 into 64, right? It is so now the hardware which is required here, so you can compare the kind of savings in the hardware. Okay, yeah, let me repeat this. Like initially I have 0 0 0 1 here into the m, and 0 1 0. I am doing 3 into 5, right? So I have loaded m as 0 3 and q as 5. M is this, and q is this, right? So I am sampling this q value of a q here. Since it is 1 here, I am going to add a and m, right? This is what this does. If it is 1 here, this m through this adder, whatever is available in a, initially it is 0, this will be added, and during the positive edge of the clock, the sum will be loaded into a. So during the positive edge of the clock, you have an m and a being added, and this is the result of m plus a. This is m plus a now. Okay, is this much clear, Shubhangi? Yeah. Okay, now after loading it, the next operation should be a shift right. So we are shifting. Now when we are, if you see here shifting, m, there is no shift operation in m. Okay, the shift operation is for this entire register together, a and q. This entire thing is a single register out here, right? So this entire shift operation. Now if you see here, this entire thing is being shifted. So this one pushed out. So this and this one from here comes here. So this is the result of the shift operation. Is this okay? Yeah. Now you have an 0 out here. Since it is a 0 out here, you are doing a plus 0 here. If it is a 0 here, last bit, you will add 0 through this mux. So the contents of a doesn't get changed. Okay. So here, so from here to here, if you see during the positive edge of the clock, the contents is not changing out here, because you are adding an 0 out here, right? So this is, it remains like this and then you are doing a shift operation. So this 1 comes out here. Here again it is 1 here. Now this time, since it is 1 here, you are doing a plus m. So this is new a plus m out here. Okay, and then again a shift operation. Then you get a 0 here. Again, since it is 0 here, you are adding just an m 0 to a. So it comes as it is, and then you do a shift operation. Is it clear now? Is it okay now? Okay, okay. So when we compare this circuit, okay, so initially what happened is during the earlier days, for a low clock frequencies, when circuits were operating at very low frequencies, then this was an okay option. Okay, because this was an operating at much faster rate in those days, because only the delays were there here, because the clock itself was slow. So you couldn't think of, because this will require, for a 64-bit multiplier, it will require 64 clock, and if your clock is in only few megahertz, then it will take that much more time for the result to come, right? Right? Whereas here it is only the propagation delay of the blocks. Only the area and power will be more. But whereas now with clocks operating in gigahertz, so even 64 clock cycles is an okay option, considering that the total hardware requirement and the power requirement is very less out here, right? So there is an we are operating in gigahertz, and so this would get finished in 64 cycles. So you can say 64 nanosecond. If it is an 1 nanosecond gigahertz, so in 64 nanoseconds, and this entire operation would get over. Okay, whereas here it again still it might get this thing. Each block might have some few picosecond delays, and it might get over it. And a few only just tens of maybe less than 10 nanosecond delay, but the that is a trade-off which you have to look at it. Okay, whether how much area and power. So and so generally the trade-off will always be in a VLSI design between area, power, and delay. How is the only one clock cycle for addition? For sequential, no, a sequential cycle, I said addition is just one clock cycle, but you have to keep shifting it like this, right, for 64 bits. Okay, so you for this thing to get completed, you will require at least 64. Here this is just a single bit adder, so you are not concerned about it. This is just not a single bit adder. It is an only single whatever 4 into 4 in this case. If you say it is just an 4 bit adder or a 64 bit adder, but total number, how is one clock cycle for addition? No, I didn't get it. For A, because this is parallel addition, right? You have this entire data available here. You have entire bit available here. This is a combinational block. So the moment this data is placed here, it will give the output out here. This is not a sequential adder. It is just a combinational adder. Is it okay? Okay. Now apart from multipliers, we have comparators and all also. And what is a comparator? There could be many uses of an comparator. First is to detect zeros, a zero detector. Okay, this is one kind of comparator where generally we use to set the flag in the microprocessor, right? After computing, if a register is 0, you need to set the flag, right? So you can make a comparator which detects all zeros, or you could make a detector which will give a high signal when all the bits are 1, or you could have an equality comparator where it compares A equal to B, and then if it is A equal to B, then the result should be high. Or you could have a magnitude comparator which compares whether A is greater than B or less than B. So you could have various kind of comparators also. So if you see here, this is an all ones comparator. So this is actually and of everything, right? So we have just put some bubbles here, so to offset those bubbles, and these bubbles has been placed here. Essentially this is all AND gates. Okay, so all ones is nothing but a AND operation of all the bits. Okay, so you can get and to get an all zero, only thing which we need to do is invert the inputs. Okay, so you will get an all zero detector. So this is an all one detector, and this is an all zero detector. So these circuits, such simple circuits, can be made to detect whether contents of the entire register, whether it is all 1 or it is all 0 out here, right? Okay, now you could also have an equality comparator. Okay, now that means if there is contents in there are two registers A and B, you want to compare whether the inputs are same or not, okay, in both the registers. So you can have a bitwise exclusive NOR, right? What does an exclusive NOR does? If it is 0 0, it will give high. If it is 1 1, it will give high, and if they are different, it will give 0. And then you use an AND operation, right? So this is known as an equality comparator. So you can do this kind of operation. You can use this circuit to check whether or not whether that bitwise, okay, it is bitwise, each bit it will compare and say whether finally the output, if A is equal to B, this will go high. Okay, so this is known as equality comparator. Okay, so now you can have an magnitude comparator also. Okay, now after this we'll take a break. Okay, so what is magnitude comparator is we are checking whether the contents are equal or less than or greater than. So all the three conditions needs to be checked. So generally we check for the first bit. Okay, normally if they are equal, then you move to the next bit, right? So that is how a normal logic works like. So this is what, and then if they are also equal, then you go to the next bit. Okay, so that is how it is done. So you start with the MSB. So let's first try and design a 1-bit comparator, and then we'll expand that philosophy to an n-bit comparator. So you have an A0, B0, right? G0 indicates that it is greater. A is greater than B. L0 indicates that A0 is less than B0. And E0 indicates that A0 and B0 are same. So we are just talking about a 1-bit comparator. Okay, so if I make the truth table, okay, for this greater than, right, this is the condition, right? This is the only condition where A is greater than B, right? This is the condition, and for less than B, this is the condition, right? So this is less than B condition, and for equal, this is the condition, right? Where 0, 0 and 1, 1. So how to implement this is it is first is okay. So if you see greater than is A0 B0 dash. Okay, greater than is A0. It is A0 bar. No, less than is A0 bar and B0, and greater than is A0 B0, right? So you can have this. And now if you see equal is an exclusive NOR. Okay, or you can also do, what you can do is OR of G0 and L0 and take an inversion of that, right? That means it is not greater than, it is not less than, and you take an it is greater than and it is less than, you take an OR and then you take an inversion. So since you are already generating these two signals, you can use these signal to generate the equality. So if I take the circuit, it will be clear to you. So this is the circuit which is used out here, right? So you have A0 and A0 bar and B0 to generate the less than signal, and B0 bar and A0 to generate the greater signal, and then you take these two signals and you put an exclusive NOR to get the equal signal. So this is 1-bit comparator now. Is this clear to all of you? Is it okay, Shubhangi? Abhishek, is it okay, this circuit? Yeah, okay. So this is an 1-bit comparator. Now if I have to expand, this is 1-bit comparator. If I have to expand it into 2 bits, okay, now what is this? Is less than, equal and greater, it is, this is less than, equal and generated, 2 1-bit comparators. Now if I have to expand it, let me, so to generate an equal, okay, for these 2 bits I have an AND operation of this these two, equal, this equal, then I will get an equal, right? So this is straightforward. Now if I have to generate greater than signal, okay, so that is if the significant G1 is high, that means it is greater, or if even if it is equal here, then if it is G0, then also I have this generator. So if you see, when I have 2 bits out here, okay, what it is, G1, that is if this is greater, okay, or if this is equal, this is greater. So is this equation clear? It is again a simple equation, right? So I can have this greater signal being generated like this, okay. this is OR of G1. That is, if the significant bit is greater, then you don't even have to check for this, you will get greater. Or if this is equal out here, then you go to the lesser significant bit, and if it is a greater out here. So this is the circuit which can generate the greater signal. And same is the case for the less than signal. Okay, if it is less, then obviously if the first bit itself is less, then it will be less. Or if it is equal and here it is less, then it is less. So the less than circuit also will have an AND and an OR. L1, that is L1 is the from the significant bit, and if even is again, if the significant bit is equal, then you go to the next significant bit and you check for the L0 condition. Now if I have to implement it, if I can keep expanding this logic for a 3-bit or for a 4-bit, like that, right? Now if you see this is the circuit for a 4-bit circuit. So what has been done here you see the less than here, right? Now let me put this. Okay, now here this is less and this is greater, and this is the equal which has been generated for each 1-bit comparators. Now you take all the equal signals out here, right? And put an AND out here, all the equal signals out here, all the equal signals you put a AND here, so you will get A equal to B output available here, right? And then you take this greater signal, this equal signal, you put a AND, and you take this L signal and you put an AND, okay, and you put an OR gate. Similarly, you take this even and you take this even, and then you put an L1 out here and you put a AND out here, right? So so you see here, if this is equal, if this is equal, and if this is less, then this becomes here. Again, you are taking this E3 equal, E2 equal, E1 equal. All the three you are going to put into one AND, and then you are taking L0 out here. So this L0 is also brought out here. So this gives the overall A less than B signal, right? Similarly, for A greater than B, you are taking this greater signal. Okay, this is most significant bit, that is straight away you are getting into the OR gate, or you are taking this equal operation to an AND gate, and you are taking a G2 and you are getting to this OR gate, or you are taking E3 and E2 to this AND gate and you are taking a G1 out here, and then you are getting to the OR gate, or you are taking E3, E2, E1 to this AND gate out here, right? And then you are taking a G0 here, and then you are getting into the OR gate. So you see this circuit, this is how it can be expanded to the N gates. Okay, you can do it just simply by making an K-map also, but that will give an because if you see here, here it is a kind of modular structure. So there is an so you can expand this and you can get a simplified circuit. Okay, so if you try to do it with a normal K-map method, so you will get a much bigger circuit. So this is one of the efficient way of implementing an magnitude comparator. Okay, so so we'll take an 10 minutes break out here, and then we will discuss about shifters. Okay, thanks a lot. Shifters is also a very vital element of all ALUs. Like shifters, although it might appear it is doing a small task, but it is very important thing. Like we have seen how a multiplier can be effectively be implemented using shifters. Like you have shifters in the multipliers. Same is the case for division, and also for say just mere by shifting you can do multiplication. Like for example, you have a data in the register. If you shift it towards the right, what is it? It is like division. If you shift it towards the left, it is multiplication by 2, right? So every shift left is multiplication by 2. The same data you push in 0, you keep moving it towards the left, it is like multiplication by 2. Like suppose you have a register 000 1, and you just shift it towards the left, it will become 0 0 1 0. That is what from 1 it has become now 2. If you shift it further, it will become 4. So you see, shifters is a very powerful tool. So let's learn how to make various kinds of shifters. Let's see what are the various shifter topologies. Okay, so you can have a logical shift. Okay, so now if you see here, a logical shift right. Okay, what it is doing is you have shift this data towards the right. So the rightmost data has been has been left out now. You and you are since it's a logical shift from the MSB side, which is now vacated, which has become vacant, I have put an 0 here. So whenever I say logical shift, whatever is the vacancy which is created, there I put an 0 out here, right? So this is logical shift left here. So 1 0 1 1. This one indicates that shift by 1 bit. Okay, it could be logical shift 2, logical by shift 3. That means those many times it has to be shifted. So this is the convention of writing it. So logical shift left by 1 bit. Okay, so I have shifted it. So this 1 has got pushed out. So 0, and then I am pushing in a 0 here. So you could have a logical shift right, or you could have a logical shift left. Okay, also you could have an arithmetic shift. Okay, arithmetic shift you can have right. Okay, right means this entire data is pushed towards the right. Now in the vacant space, the sign is preserved. Okay, so you have, since it was a negative number here, 1 represents a negative number, again you have an 1 out here. Okay, so that is the sign is preserved out here. So obviously arithmetic shift left is this doesn't have any meaning, right? Okay, because even if it is pushed here, you won't put an 1 out here, because that changes the data itself. Okay, so you don't have arithmetic shift left. Even if someone writes it like that, in the left operation you have to push a 0. So this is not a sign bit, this is an data. Only the right bit is a sign bit. So whenever you are shifting it towards the right, so the sign bit can be preserved in an arithmetic shift right. Okay, if you see here 1 0 1, in a 2's complement, if you just see, if it's a 3-bit 2's complement, 1 1 0 1 and 1 1 1 0 1 and 1 1 0 0 1 1 0 1 will, if it's a 3-bit number, okay, 2's complement 1 0 1 is same as 1 1 0 1 in a 4-bit complement system. Okay, so that arithmetic sign extension doesn't change the value of the number. Okay, whereas in the left we always have to put 0, because otherwise it is going to change the sign of the number. Okay, then you could have an rotate operation. Rotate is just taking this bit and rotate right means from the right hand side you take 1 bit and you put it back from the left. So you find here this has been shifted here. So this one has come here. Okay, similarly you could have an rotate left operation also. So these are the various kind of shift operations which we require to do. So how they can be implemented, and this is the binary shift adder if 1 bit needs to be shifted. So there are 3 control signals. No means no operation or no shift, and then you have a right shift and you could have a left shift. So if you see no operation means this particular transistor will be switched on. So AI is going to come towards B. This is a buffer. So AI comes out as BI and AI minus 1 comes out as BI minus 1 if no. Now if I activate the left signal out here, so this transistor will be switched on. Now if you see here AI now gets routed, AI minus 1 gets routed to BI. And similarly this input whatever is available here, that gets I minus 2 will get routed to BI, I minus 1. So it is going to shift towards the left. Similarly if I have a right operation, right shift signal going high, so this transistor will be switched on. So BI plus 1, AI plus 1 will come here to BI, and this signal, okay, since this right is operated, AI will get routed towards BI minus 1. Okay, so this is how by using pass transistors we can do the shifting operations, right? Now if I have to do a multi-bit, I cannot keep cascading one like this in series with another one. If I keep doing it, no, then the propagation delay will be very high. So I cannot cascade. So I should do some kind of a parallel operation for it to be fast. Otherwise, it will become very slow. So there are two types of parallel configurations. One is known as the barrel shifter. The other one is known as an logarithmic shifter. Okay. So this is what a barrel shifter looks like. Okay. If you see here, these are the lines which are this is the line which is connected to each of the buffer, and these are the input lines A0, A1, A2, A3. Now suppose the shift, this is the shift 0, shift 1, shift 1, shift, these are the control signals. If the shift 0 signal is high, so what happens is this transistor will be activated. So I have A0, through this signal it is coming to B0. So again you will find this transistor is brought here, and again you have this signal, this is connected to this here. So I have this A1 out here being connected, so it is going to come to B1. Similarly this transistor, so you will find an A2 through this transistor, it is coming to an B2, right? Similarly A3, so A3 it is going to come here, this transistor is switched on, it is going to come to B3. So it is not shifted by. Now if I have shift 1, now you will find A1, this transistor is off now, this transistor will be switched on, right? So you will have this signal coming from here. Okay. No, yeah, this shift, it is shift 1 signal is there. So this is going to this is shift 1. Okay, this transistor will be switched on. So it will be from the A3 will be coming out here, and it will come to B0. Similarly, it goes out here. A1 will be coming here, right? A1 will be coming. This is this transistor coming here. So this A1 will be coming to B0, and A2 will be coming into B1, and then similarly you will have an A3 coming through this transistor to the B2. So this entire bit is going to get shifted. So this is how, by using 1, 2, 3, 4 series transistors out here, you can make the shift operation. So this is parallelly for each line you have 4 transistors, and each of these transistors is connected by like shift 1 transistor is going to get an A1 signal from here to this B0, right? If you see here, shift 2 is going to get from A2 signal from here, from this line here to B0. Shift 3 signal is again from A3, it is going to see this vertical line, it is going to get here, right? So that's true for each of the bit. Now shift 1, now when I put a shift 1 out here, so you see these vertical lines, you will have to check for these vertical lines and these transistors. So it is like placed in the layout wise, it is placed in a symmetrical manner. So and that is why these signals, these have been placed in this manner, so that you make the optimum layout. Okay, so that is why this shows the gate connections. Actually these dotted lines shows the gate connections, right? So shift 0, this transistor will be switched on, so A0 would be coming to B0. Shift 1, this transistor will be switched on, so you have an A1 being connected here. Shift 2, the third transistor A2 will be connected out here. Okay, similarly shift 3, this will be connected here, right? And this same shift 0 is available here. So in shift 0 you will find an A1 is getting connected to B1. This transistor will be switched on. So now if you see here, A2 is going to get connected here. This transistor will be switched on. So A3 will be getting connected here for shift 0. So similarly, for if I talk about this particular in shift 1, so shift 1 transistor is coming here, right? So in the shift 1 you will find A2 is getting connected here to B1. Okay, so that is how this is the layout which is done in a symmetrical manner. Is this operation clear to all of you? Yeah, Aman, is it okay? Okay. So this is the layout of an barrel shifter. Okay, in the layout, in your VLSI classes, you might have studied that each of these wire widths, okay, or it could be the poly width, is generally 4 lambda, and lambda is, what is lambda? Lambda is actually half of the technology. Like for 2 lambda is generally the width, okay. Like for a 45 nanometer, lambda is 22.5. Okay, so that is the so generally we express the minimum DRC check rules using a lambda parameter. Okay, so 4 lambda means, like for a 45 nanometer, 2 lambda is 45 nanometer. So at least this width has to be of 4 lambda, that is 90 nanometer, for this line to be fabricated properly, and between 2 lines at least there has to be 4. So this 4 lambda plus 4 lambda gives the this is known as the pitch. Okay, that means this one particular line actually occupies, although this width is only 4, okay, it actually occupies 4 lambda space in the chip, because you have to give another 4 lambda space. So this 8 lambda together will be called as an pitch. Okay, so now if you see, when in the barrel shifter, okay, so you have these lines going like this, right? All the gates are connected like this. So you will find the width of these gates or the metal lines has to be 4 lambda, and also the spacing here, okay, it has to be 4 lambda. So the total, if you compute the total width required for a barrel, is actually 2 pitch. This is the pitch. PM is the pitch, that is 8 lambda into M is the number of shifts which are required. So this is the kind of space and barrel shifter takes. Okay, so this is how an ideal, it is the most ideal way of doing a layout which will require the least amount of space. Okay, so this is known as barrel shifter. Okay, you could also have an logarithmic shifter out here. Okay, what is a logarithmic shifter is, like here for each shift I had one bit, right? I didn't, in this shifter 2 lines going high has not been catered for, right? Only one line has to go high. So you require an decoder here, and then you can have only one line going high. But this is not the case here in logarithmic shifter. So if suppose it is 0 0, there are 2 lines here, shift 1 and shift 2, and let's just talk about the 2 bits and try to understand the operation. If both the shift 1 and shift 2 are 0 0, then you have A0. Okay, this bar line will be high here, okay, because this is 0, and this shift 2 bar line also will be high. So this transistor will also be high. So A0 is coming straight away to the B0. Okay, now suppose the shift 1 line is high, so this transistor will be switched off now, right? This is switched off, so A0 cannot go. Then what can go? This is become high now here, shift 1 high, so A1 will be routed here now, right? Similarly A2 will be routed here, A3 will be routed here. So you can have the second combination like this. Now suppose I have shift 1 0 and shift 2 going high. In that case you will find here shift 2 transistor, this is going high, right? So this is going high out here. So I have now A3 line. If you see here, this is coming from the A3 line, this is coming here to A2. So 2 shifts is happening out here, right? Now suppose I have shift 1 also going high and shift 2 also going high, right? Then I will have, okay, both the signals being high, so I will have this A3 line going high. So it is coming from here, it will come from here, again it is going to come from the shift 2 line out here. So you will find 2 bits of shifting is happening when both these lines are getting switched on. So what is the application of 2 shift going? Like I with 2 bits I can do either 0 0 shift, or I can have total 4 different kinds of shift with 2 bits. Okay, 2 shift means it will, if I have 0 0, A0 will be shifted, will be brought to B0. If I have 0 1, I will have A1 being brought to B0. If I have 1 0, I will have A2 being brought, and if I have 1 1, I will have A3 being brought to B0. Okay. So if you see these interconnections, and if you try to see what happens if both shift 1 and shift 2 are high, then you will find A3 being brought to B0 out here, right? If you can track that circuit, see A3 shift 1 is high, so this transistor is high, it will come here, right? And then this is off out here, so it will come here and shift 2. So if you just track this signal, it will come from here. This transistor is on, so that will come here. Now straight away A3 is finding a path when both are high to come to B0 through this transistor and through this transistor. So that is the way you can have 4 different combinations with just 2 bits. In the previous case, you could have only 2 different combinations, right? So here in the logarithmic shifter, you can have 4 different combinations with just 2 bits. Okay, so here the routing is slightly complex. Okay, but then you can have a maximum number of various combinations of shifts using minimum number of control lines. Okay, so that is the advantage. Is it okay, Shubhangi? Yeah. Okay, we can actually make much more efficient shifters using multiplexers. Okay, so now this is the multiplexer, and this is the output register. These are the parallel inputs which are available. Okay, now suppose these are the control lines. Okay, these are the control lines. If I give 0 0 out here, okay, if I give 0 0, what happens? You have this A data, previous data which is available, which is coming to here. Again you have this previous data which is coming to 0, previous data which is coming to 0, so previous data coming to 0. So if I give 0 0, whatever is the previous data, that will be available here. Now if I give 0 1, what happens, right? If I give 0 1 out here, this data is coming out here. What is correct? It is it will take a serial input out here from here, right? Okay, it will take a serial 1 output. Here what it is going to take? It is going to take this 1 is taken from the previous stage. Here it is taking 1, it is taking from the previous stage. Here it is 1, it is taking from the previous stage. So if I give a control signal 0 1, okay, what it is going to do? It is going to shift this entire data in this here. Okay, it is going to shift the previous data, whatever was available, towards the right. Is it okay with all of you? Right? If I give 0 1 here, if you see here, this data is 0. This is the register, right? This previous data is available here. Okay, that is going to be okay. The new you can give here 0 for logical shift, but if you see here, this 1 is coming from the previous bit. So whatever data was available here, now during the next clock it will come here, right? Because this 0 is going to come here through the 0 out available here, and that is given to 1 also here, right? So this output is given to 1 here, and from here it will be given here. So this 0 is going to come to the 1 here, from 1 it is given here. So it will do an shift right operation, right? Similarly, if I give an 1 0 out here, okay, then the 2 will be activated. Now what is 2? Now this output is given here to the 2, right? And this output is given here to the 2. This output is given to the here. So it will do an shift left operation, correct? So this will do an shift left operation. Okay. Similarly, if I give a 1 1 out here, so if I give 1 1 out here, what happens? It will be 3 will be activated. So all the 3. So you have an if you have an parallel inputs, so all the new this will be filled with a new data. So so this new data will be filled, and then you also have a clear signal. You can here Okay, as asynchronous, this is the clock signal. Okay, you can have a clear signal where to clear all the registers. So you see this particular configuration can do lot of things. One, you can clear the data, you can load a new data, you can keep the data as it is by giving 0 0. You can preserve the data, or you can shift it towards the left, or you can shift it towards the right. Okay, so this is an multi-purpose shift register using a sequential circuit. Is it okay with all of you? So you see again, as the clock frequency is going high, so we can start using sequential circuits, replacing some of the combinational circuits. So this is doing the same function of this. So you see it requires much lesser space out here, because this is an much simpler, and this is doing this we are talking only about a shift in one direction. If you have to do it in shift in two directions, you can imagine the complexity here, whereas these circuits are pretty simple. Okay, so with that, I will stop it here for today. So we'll meet again next week. Okay, thanks a lot.